Today we will start chapter 8, which is shear and diagonal tension. This chapter name is not so clear. Simply we will learn shear reinforcement design. So what is shear reinforcement design, how to design it? So in this video I will cover this theory, and in the next video I will solve an example. So if I uh, so here what I did, I drew a beam and there's reinforcement here. So it has some load, and whatever the load is, the shear force diagram is similar to this, assume it is. Then in this beam, what is D? D is the distance from compression phase to the reinforcement. The reason I'm showing D here, because we need this D many times, and I get this question every time whenever I teach this subject. So I am showing D here again. Now, what is shear failure? Shear failure is typically from D distance from the support, and it is a diagonal type failure. Diagonal failure, angle is 45 degree. Now every time it will not be 45 degree, but based on experience we found that the shear failure is typically diagonal and it is 45 degree, and it occurs at d distance from the support. Now this is why in this shear force diagram the maximum shear force is this value. But when we design, we do not consider this value. We consider our shear force at d distance. Whatever the shear force here, that we name it VU. This is our design shear force. This is our design shear force. Now again, whenever we are drawing shear force diagram, here the maximum shear force is not our design shear force. The shear force at d distance from the face of the support is our design shear force. So that is something to remember. Now again, what is d? I am already shown here what is d. So now you know what is d. Now why shear force is diagonal? I drew here a profile. If I take the take this profile here, you can see I have some main reinforcement and I have some shear reinforcement. So shear reinforcement have some force, main reinforcement have some tensile force. The combined effect of these two force is similar to this. This is the resultant of these two force, 1 and 2. Resultant of these two force is this way. This is why we get a crack similar to this. Now it is not always linear, it is roughly linear, diagonal, and acts at 45 degree. Now by 45 degree I mean that if this distance is d up to this reinforcement, this distance will be also d if this angle is 45 degree. We need to know this concept. So hopefully from this portion at least you learn that how to design shear force reinforcement. Not detail, just the overview, that whatever your maximum shear force is, that is not the design shear force. At d distance, whatever the shear force, that is your design shear force. And why d distance, I am showing it here. Why it is at d distance? Because shear failure occurs at d distance. And the why shear force is shear failure is diagonal, because the combined effect of this shear force here and the longitudinal force here. Okay, now we will see some okay, so if I do this now, whatever the shear force I have designed shear force, who will take this shear force? If I draw the beam again, my beam has some concrete, so this is concrete, and I have the shear reinforcement this way. So I have two things, one is concrete, one is steel. So who will take this shear force? Some part will be taken by concrete, some part will be taken by my shear reinforcement. So we can write our equation is whatever our design shear force, concrete will take some, so this is concrete portion, and steel will take some, that is our steel portion. C means concrete, S means steel, the reinforcement. Why I used phi? Because it is design. As design, we use phi as a strength reduction factor to decrease our capacity to be safe. Now, if we use the nominal equation, it will be BC plus PS. Now, if I use multiply phi here, multiply, sorry, multiply phi here, multiply phi here, it will be this equation. So, this equation we use it in our design. So, at least from this equation, you learn that whatever your design shear force, concrete will take some, your reinforcement will take the rest. Now, how much concrete the plain concrete can take? So there are different testing. Based on the testing, we found that concrete can take, again remember this value, twice phi lambda, lambda phi a prime c b d. Sometimes we write bw, simply that bw means this one. Sometimes we write b, that is okay. Bw, if it is a t beam, then we use bw. So whatever it is, this b means this width of the beam, d means the depth of the reinforcement, depth of distance from compression phase to the reinforcement, that is d. And what is p is strength reduction factor. What is lambda? Lambda means if we use lightweight factor, then that is counted by lightweight aggregate factor. If our aggregate is lightweight, then we use this factor. If we do not use lightweight normal weight concrete, then lambda is 1, or you can simply delete it. So memorize this equation. If you cannot memorize, at least know that there is an equation to calculate the capacity of plain concrete for shear force. So concrete can take this amount of shear force. Now whatever shear force I have, concrete will take some. If there is remaining, I need to provide reinforcement to take it. Okay, so what we learned? We learned that VU is phi VC plus phi VS. Then how much phi BC? Phi BC is 2. I am now not using the lambda anymore, so I am using plain normal concrete. If it is a lightweight concrete, you can use that, no problem. Then how much VS will be? So PVS will be VU minus PBC, and then VS will be VU minus PBC by phi. Again, we need to use this equation somewhere when we will calculate the distance. So hopefully you understood this equation. This is the capacity of a plain concrete, and this value is based on testing or experience, so there is no scientific answer, and this is just a mathematics. Total design shear force, concrete will take some, steel will take some. Then if I rearrange, the contribution of steel in shear force is this equation. We need this equation. So remember these two equations. Now I will go to your book, how to calculate the spacing. So in your book there is an if I go down to your book here, the total shear force taken by concrete is area of the shear reinforcement, yield stress of the shear reinforcement, and number of reinforcement. That means if I oh, it is here already, yes. So the crack is here, the crack is here now. So what is the shear force taken by this steel, this 3 steel? How to calculate this is whatever the reinforcement used, the area of reinforcement, which is AV, area of reinforcement used, times the stress, yield stress. So area times stress is force, times N. That means how many bar we used here? We used here 3 bar, or whatever the bar is, N. So total shear force taken by the steel in this failure zone is this. Now what is the number of bar? number of bar is this distance divided by spacing. So whatever the d is divided by spacing is your number of bar. Then if you insert this value of n here, you will get the equation of spacing. Now you do not need to memorize this, is just to understand if you want to understand uh, this equation. So this equation we will use it. Now where we got this equation, that is the explanation. So if I write the spacing equation is area of shear reinforcement times yield strength of the shear reinforcement times d divided by I forgot here, or Vs. Yes. So this is the spacing required. Spacing required. So this equation, these three equations are very important. This is the capacity of concrete. From this you can calculate the shear force required by steel. Then from the required steel you can calculate the spacing required. Spacing means see in this beam whatever the spacing of the shear reinforcement, this is your spacing. So these three equations you need to understand what is now, what is AB, area of shear reinforcement. So this is your beam reinforcement. Here you are using this reinforcement, the area of these two bar, the area of this bar and this bar. Say if it is number 3 bar, then here your area will be 1 here, 2 here. So 2 times 0.11 inch square. If you use number 3 bar, I can memorize that number. For number 3 bar, the area is 0.11 inch square. So 2 here, so 2. What is your yield stress? Whatever the material you are using. If the reinforcement is 60 grade, then 60 ksi. Now what is D? D is distance from here to here, D. And what is Vs? Whatever the shear force required to be carried by the steel. How to calculate? Using this equation. So hopefully you understood the concept of shear reinforcement design. You will choose a bar, number 3 or number 4, then you will calculate the spacing. Now you know that there is a code requirement to provide the minimum amount of reinforcement. We cannot provide less than minimum. So to account that, what to do, I listed here a table. Now this table, it is not in your book. This table I got it from your AFE reference handbook. So AFE reference handbook, page number 277, and the version of the book is 10th version. Now whatever the AFE reference handbook you use, this table is there. Why this table I brought it here? Because this table summarized everything in a table, so that it is very easy for you. So I will come back here. Before coming back, now we'll go to our shear reinforcement design theory. Say this is our shear force diagram. Shear force diagram. Okay, shear force diagram. So this is our V max. Now this is our V max. We do not design based on this. We calculate the shear force at d distance. At d distance we calculate the shear force VU. That is our design shear force. Now how much concrete can take? Concrete can take PVC. So we will locate PVC somewhere. Say PVC is here. So PVC we will locate it and we will calculate this distance. Now what does PVC means? Means my concrete can take this amount of shear force. Now anything here, actually we do not need any reinforcement because my concrete can take this shear force. But ACI code says be safe, provide shear reinforcement up to PVC by 2. So calculate this distance. Now in this region we do not need any reinforcement, but ACI told I, okay, I am writing here ACI. ACI recommended still the use some here. Any area with shear force less than this, no reinforcement required. No reinforcement required at all. Even your code did not say provide reinforcement here. You can provide some reinforcement here just to tie the bar, but you do not need it. In fact, you do not need in this region also. You only need reinforcement here. but here we will provide just to satisfy ACI requirement. So if I give it name 1, name 2, name 3, name 4, name 1, we will not calculate shear reinforcement here because my shear failure is not here. So what we will do, whatever the spacing we will select here, the spacing we will paste here. Then we will calculate our spacing here also. We will calculate spacing here. Here we do not need any reinforcement. Now how to calculate spacing? That table will give you the summary. Okay, so before using that table, make sure you need to draw this shear force diagram. Draw the shear force diagram, locate the design shear force, locate the PVC, locate PVC by 2, and locate it and calculate the distance. Then calculate the required spacing here, calculate the required spacing here, and whatever is here, copy paste here. And based on the required spacing and the maximum allowable, choose a convenient number, round number. Say your required spacing is say 9.3 inch, say, and your maximum allowable, how you will find, I will show you. Say maximum allowable is 12 inch. Now what you will provide here? Will you provide 9.3? 9.3 is okay, but I will provide say 9 inch. I will say 9 inch to choose a round number so that my levers, when they will place it, it will be easier for you. Okay, then I will go to the table. This table again here. When my shear reinforcement, shear force is more than PVC. More than PVC, what does it mean? That means I am here. This is PVC. My shear force is in this region. So reason number 2. So this is reason number 2. If reason number 2, calculate Vs by this equation and then calculate the required spacing using this equation. How to find it? AB, you will assume a number of the bar and then calculate the area. Fy typically known, D known, Vs you will calculate here. So this is the required spacing by calculation. This is, oh no, not this one. This is the maximum allowable. Now if your Vs is less than this equation, you have to calculate that also. If your Vs is less than this equation, your maximum possible is D by 2 or 24 inch. If your Vs is more than this, then the required maximum spacing permitted is D by 4 or 12 inch. Then your case will be that this or this. So take a number from here, take a number from here. Based on these two consideration, choose a spacing of the reinforcement. And then for other reason, that means this reason, number 3, which is more than PVC by 2. For PVC by 2, this is your column. So calculate your spacing using this equation and or this equation. So calculate your spacing. Then maximum permitted is this or this. Now based on this, choose a round spacing. Now here we will provide the minimum amount of reinforcement. The reason is, in this region we actually do not need any reinforcement. We are just providing to be safe. So again, this column is our this column where we do not need reinforcement, but we will provide. So okay, I will wrap up here. In the next video I'll show an example, but again if I do quickly here, that draw your shear force diagram, shows your PU at D distance, then locate your PVC by 2 in this region. We do not need any reinforcement. We need here some, because code says here we obviously need the reinforcement. Whatever the spacing we will get here, we'll copy paste here. Now if say something else, say this value is 15K, whatever is, but if you drew your shear force diagram and the maximum value say 12K, and so then in this maximum shear force 12, this value is 15. Do we need reinforcement? Actually no, but still we should provide up to this. So we will locate PBC by 2, that means 7.5. 7.5 is roughly here, 7.5. So and calculate D. In this region we will provide the reinforcement. Now other case, maybe say in your shear force diagram is this maximum value is say 6 kip, and what is this value 15, this 7.5, that means actually you do not need any reinforcement. Something else I did not tell you that very quickly. So VS cannot exceed more than this value. For some reason, if you get your VS more than this value, your section is not adequate, because you still cannot take more than this. This is why if I open the table here, oh, it is not in the table, it says just less than 4 times or more than 4 times. But if it is more than 8 times, our section is not good. So if our shear contribution of shear force per still is more than this, our section is not adequate. We need to increase B and increase D. Okay, so long story short, this is the theory of shear reinforcement design, and in the next video I will show you an example. Thank you.